Hello students, good evening all. So welcome to our next session. So this will be our third session on this particular chapter, definite integrals. So far we have covered the basic introduction of this particular chapter, definite integrals, as well as the properties. So today will be our last session of this chapter, definite integrals. So let's just have a quick introduction, like overview of what and all concepts we are going to cover in detail in our today's session. Right, so first we'll just have a quick recap what we have covered so far in our chapter of definite integrals. Right, so we have started with the definition, like introduction part to our definite integrals, like what is the typical representation of it. So those typical things we have already covered. And in the later part, we have started discussing the basic properties of integrals, which involve, like we have seen questions, even we have solved questions related to those properties of integrals. And we have even covered some special properties like reflection property, shift property. So those and all we have covered. So all typical properties which are in our definite integrals. So everything we have covered in this topic of properties of integrals. So coming to our today's session, we are going to deal with some special integrals. So if you remember, in the last session itself, we had a quick discussion of this special integrals. So what are these special integrals we have started? So they are mostly related to our trigonometric functions, sine and cosine functions. Right. So if we are having a typical representation of integral, so how can we solve and how can we get the answer, easily get the integral value within some seconds? So using this some special integral. So that we are going to discuss in this some special integrals. In this we are going to see the Wallis formula. So two things we are going to learn in this some special integrals. One is Wallis formula and the next one is gamma formula. Right, so these two will be helping us to get to find the integral value in a easier way. Right, so after learning this some special integrals, which are nothing but our Wallis formula as well as the gammas. So the next we are going to do the topic that is nothing but limit as a sum. So this will be our last and final concept in this chapter of definite integrals, which is limit as a sum. Right, so what is actually this limit as a sum? So we are going to convert this limit and all into our integrals. So into our definite integral, so that it will help us. So instead of finding this huge some value, limit of some value, we can convert that into our definite integral format and we can easily simplify it and get the limit as a sum value. So how we are going to do that? So we are going to learn here in our last concept as our limit as sum. So as usual, as for specific concepts, we are going to do the corresponding questions. And at the last, I have added questions from JEE papers. So first we are having the questions from recent 2020 JEE paper, and then we are having questions from previous years and also that are also added here. So after these two concepts, we are going to do the questions from our previous mains level so that you can have a handy with what typical types of questions we can expect from this definite integral in our mains point of view. Right. So let's start with our special integrals as I mentioned. So first we are going to start with the first formula, that is Wallis formula. Right. So what are the conditions here for this Wallis formula? So let's just have a look here. So the integral, the format of the integral should be either of this form or it can be of this form, which means the limits. So here you can observe the limits should be always 0 and pi by 2. So here 0 and pi by 2, 0 and pi by 2, which means the function should be always continuous in this interval 0 comma pi by 2. And the function here sin power nx dx, or else it can be cos power nx. Right. So the n value will be an integer. Right, so it's a positive integer. It can be a even integer or odd integer. So correspondingly for even we are having a separate formula, and for odd positive integer we are having separate formula. So let's see what are the formulas corresponding to the value of when it is even positive integer as well as when it is odd positive integer. So before getting into the n value, whether it's even or odd, we have to check with two things. That is the limits of the integral, they have to be 0 and pi by 2, as well as the function. It can be either sine or it can be cos. Right. So this will be the standard formats of the functions of the integral we should have to apply our Wallis formula here. Right. So now let's get into the n. So what happens? What will be the formula when the n is odd positive integer, this one, and when n is a even positive integer. So let's have a look over here. When n is a odd positive integer, our format of formula, that is our Wallis formula, will be, it starts from n. So it will be two steps here. We'll be having numerator as well as the denominator, and in the numerator we'll be starting the values from n minus 1. Right, and then n minus 3. So it like we'll be subtracting the odd numbers. So n minus 3, the next will be n minus 5 until we will be having, it can be 1 or 2, depends, it will be until 2 because it shouldn't be less than 0. It shouldn't be 0 or less than 0. So until that we can stop the value. And the next in the denominator, in the numerator we have subtracted the odd numbers, whereas in denominator we are going to subtract the even. So we'll be starting with n, and the next n minus 2. Next n minus 4. So the same thing it will be going on. So this is for when n is a odd positive integer. If n is a even positive integer, the steps of this numerator as well as the denominator, they will be the same. So along with that, there will be one more term added when n is a even positive integer, that is nothing but into pi by 2. So the whole term into pi by 2 will be multiplied when n is a even positive integer. Right. So this is the difference when n is the odd positive integer and when n is a even positive integer. So instead of taking or applying our property like 0 plus pi by 2, so in place of x we can write pi by 2 minus x, and we can simplify it, and then we can add and we can integrate. So instead of doing all these steps to get the integral value, we can directly apply the Wallis formula here and we can directly get the value, definite value of the integral here. So it's as easy as that. So let's see some questions here for the Wallis formula. So here comes the first question, guys. As I have explained the procedure clearly, I hope you can do it by your own. So let's give it a try and let me know what's the answer here. Quickly you can, so what are the steps we have to look into it before applying our Wallis formula? We have to check for the limits whether there are 0 or pi by 0 to pi by 2 or not. And the next we have to check the function. It can be either sin power nx or cos power nx. and then we have to check the n value whether it's a even or odd. Accordingly, we have to apply the corresponding Wallis formula here. So let's see. So if anyone got the answer, please let me know. So I'll be writing the general format here. So the integral format can be 0 to pi by 2 cos power nx dx, or it can be a format integral 0 to pi by 2 sin power nx dx. You can compare the given question, and again corresponding for even and odd, we'll be having the formulas. If n is odd, then what is the formula? It will be n minus 1, n minus 3, n minus 5, and so on until we should be ending with a positive value. And then here n minus 2, n minus 4, and so on. If it's odd, there will be no multiplication here. If n is even, if suppose n value is even, then it will be, the other terms will be the same, the numerator and denominator, n minus 3, n minus 5, and so on. Here same thing, n minus 2, n minus 4, and so on. But additionally, we will be having a pi by 2 multiplied to the whole term here when the n value is even. So you can compare the formula, that is our Wallis formula, to the given question, and you can let me know what's the answer here. So if anyone got the answer, please let me know. So by based upon the thing, so let's just verify the conditions. So the limits here are 0 to pi by 2, first condition satisfied, and the function here is in terms of cos power nx, it's also satisfied. And what is our n value? So n is odd, so what is the formula which we have to pick here? So this will be the formula which we have to pick, and we have to write the answer here. Quickly guys, I have given the formula here, just the application part here. So here, what is the n value according to the question? N equal to 7. Okay, 16. 16 divided by, what's the answer? Okay, Shyam has given the answer. Okay, good. So let's see for two more answers. Quickly guys, just a formula application, simple. So here, what is our n value? So n value will be 7, and which is the odd number. So this will be the formula which we have to apply. So the numerator, so we'll be having numerator as well as denominator. So numerator will be started with n minus 1. So 7 minus 1, 7 minus 3, and then 7 minus 5. So we can't take 7 minus 7 because that will become 0. So we'll be ending before 0. So here in the denominator it will be 7, 7 minus 2, and then 7 minus 4, and then 7 minus 6. So we'll be ending here, that will be 1. So 7 minus 1 will be 6, 7 minus 3 will be 4, 7 minus 5 will be 2. And in the denominator 7, 7 minus 2 will be 5, 7 minus 4 will be 3. 7 minus 6 will be 1. So here 3, this will cancel 2 times. So if we multiply, 4 2s are 8, 16 in the numerator as well as 7 into 5, 35 in the denominator. So the definite integral value which we are having here is nothing but equal to 16 by 35. That's the integral value here. So I hope you guys got it. Okay, Arun also given the answer. Lakshmi here. Okay. So let's move on. So let's move on to our next formula here. That is, we can say gamma function. Right. So even for the gamma function, we'll be having the corresponding standard form of integral and based upon the m. So here you can observe for gamma, we are having two values. So initially for our values, it will be only one n. So one thing, but here we'll be having two m and n. So corresponding for m and n, we'll be having two formulas here, the same as the previous one. Right. So let's see what is the standard format of the integral here. So the limits are 0 to pi by 2. So that's constant. So the limits again, they should be 0 to pi by 2, 0 and pi by 2. And the format of the function should be, so initially it is only one function. So either it can be sin x or either it can be cos x. But now if you observe, it's combination of both the functions, sin as well as cos. So our integral here, the definite integral is having both the functions, sin as well as cos. So the standard format of the integral here will be integration from 0 to pi by 2 and the function here will be sin power mx into cos power nx. So here we will be having two unknowns, two variables, that is m as well as n. So based upon the values of m and n, we will be having the corresponding value, corresponding formula for our gamma function. Right. So here comes the first function. If m and n both are not simultaneously even positive integers. Right. So there is two possibilities here. That means the first case states that both m and n are not even positive integers simultaneously, which means one can be even, the other can be odd. But both cannot be positive, even positive integers. If that's the case, then this will be the, okay, Siddharth also given the answer, 16 by 35, okay. So if that's the case, when both m and n are not simultaneously even positive integers, then this will be the formula we'll be using accordingly. So what it states, so in the numerator, we'll be starting with m, same as odd numbers elimination, that is m minus 1, m minus 3 and so on until it can be 2 or 3 based upon m value. Similarly for n also, that will be n minus 1 into n minus 3 and so on until it can be until 2 or 1. And in the denominator, so initially what it is, it will be even elimination, that is n, we started with n and then minus 2 minus 4. Here the same thing, but here we are having two m and n. So we'll be starting, instead of n, we'll be starting with m plus n and then m plus n minus 2 and then m plus n minus 4. So until either it can be 2 or 1 based upon the m and n values. So this will be the case, the first case, when our both m and n values are not simultaneously even positive integers. So this is the first case for the gamma function. So let's see the second case. That means what happens if both m and n are even positive integers. So what is our standard integral format? So limits 0 to pi by 2. So the function will be sin power mx into cos power nx dx. So in this case, that is my case 2 for gamma function, where my both m and n values are even positive integers. So initially what we have done, the same will be done here. That means the numerator and denominator will be the same format. So we'll be starting with odd. So m minus 1, m minus 3, m minus 5 and so on until it will get 0, 1 or 2. And then for n, n minus 1, n minus 3 and until it will end up getting 1 or 2. And the next in denominator will be starting with sum, that is m plus n and then m plus n minus 2, m plus n minus 4 and so on until we get the number 2 or 1. Right. So as here we are having both m and n values are positive integers, at last we'll be multiplying with the pi by 2 here. So for initial case, for our Wallis formula, if it's a even, then we are going to multiply with pi by 2. Here both are even positive integers. When both m and n are even positive integers, then we are going to multiply with this pi by 2 here. Right. So this is our next formula, that is our gamma function. So these are two special integrals which we actually make our solution, finding the integral value easy when we have these kinds of integrals of sine and cosine functions. So these two are our special integrals here. So gamma as well as Wallis. So let's do questions related to this one. So here comes the question. So quickly try and answer this. So this is according to our gamma function. So first, what are the things we have to verify? We have to verify whether they are satisfying the standard conditions of integrals of our formulas or not, and then we have to proceed and applying the formula. So here we are having both sine and cos functions. So by looking at it, we can say that this is related to our gamma function. So we have to check the conditions of the gamma function here. So what are the conditions of gamma function? The standard integral should be 0 to pi by 2 sine power mx and cos power nx dx. So if these both m and n are not simultaneously positive integers, then what will be the corresponding formula? It will be m minus 1, m minus 3 and so on into n minus 1, n minus 3 and so on. And in the denominator, it will be sum of these two, that is m plus n into m plus n minus 2 and m plus n minus 4 and so on until we'll be getting either 1 or 2. Right, so this is the formula. Okay, Shyam and Siddharth has given the answer. Okay, 8 by 315. Okay. So what about others? Okay, Arun also given. Okay. So let's see how we can apply this. So here we can see the m and n value both are not simultaneously positive. So we can apply the first formula, that is, so 4 minus 1 and then 4 minus 3. So we can end it here. And then 5 minus 1, 5 minus 3. So we can end it here. And in the denominator, 4 plus 5, that is 9. And then 9 minus 2, 9 minus 4, 9 minus 6, and then 9 minus 8. So there is no need to multiply with pi by 2. So here what will be the term? 4 minus 1 will be 3, 4 minus 3 will be 1, 5 minus 1 will be 4, here it will be 2. So here 9, 9 minus 2, 7. So here it will be 5, 3, 1. So this 3 and this 3 will be getting cancelled and we'll be having 4 into 2, 8. So 7 into 5, 35. So 35 into 9 will be 315. So this will be the integral value here. So which is equal to directly 8 by 315. Right, I hope most of you has given the answer already. So let's move on to the next question. So here comes the next question, guys. So you can observe the question, and you can use your properties and convert that also, and then you can apply our special integrals. So by applying our properties which we have learned before earlier, so we can actually convert this into our special integral format, and we can apply the formula. Because here our limits should be 0 to pi by 2, but here limits are 0 to 4 pi. So we have to think that can we actually convert the limit to pi by 2 or not. So that will be our first thought we have to get into our mind. So did anyone got the idea how to convert this? So we are having the property, right? So in place of x, we can substitute this 4 pi minus x. And then we can check if it's giving the same function, then so we are having this format 0 to n pi. Right, so this n will be coming here. So that is the property which we have learned. So here it's a sine power 8x. So it will be remaining as it is even if I substitute this. So I can write this to be, this n will be coming here. This will be turning out to be 0 to pi sine power 8x dx. So the same thing again here. So if I have this pi, if I can substitute, right, so if I can substitute and it will be remaining as the same f of x, then how can I rewrite? So I can rewrite to be, so if I having I'll just write the property here. If I'm having a function 0 to pi f of x dx, so even after substituting my x in place of x, if I substitute pi by x, I am remaining, that means my f of pi minus x will be equal to f of x. Then I can rewrite this integral to be 2 times 0 to pi by 2 f of x dx. Right, so we can apply the same format here, because sine power 8x, even if you are having a negative, that turns out to be positive. So this can also be rewritten as 4 into 2 into 0 to pi by 2 sine power 8x. So here we have applied our basic properties of integrals which we have learned and converted this into our special integral format, so that we can apply our Wallis formula here. So now what is our integral after conversion? So it turns out to be 8 integration to 0 to pi by 2 sine power 8x dx. Right. So now this typical integral has been turned out to be 8 into 0 to pi by 2 sine power 8x dx. So now we have to apply our Wallis formula and let me know what's the answer here. So if you don't remember the properties, so let's get you can get back to the properties later and you can have a look over the properties and then you will be understanding easily how we have converted this. So now from this we have converted our integral to 8 times 0 to pi by 2 sine power 8x dx. So now you know how to apply the Wallis formula. So here limits are same and sine function and here is even. So how we'll be writing? 8 minus 1, 8 minus 3, 8 minus 5, 8 minus 7 and in the denominator we'll start with 8 and then 8 minus 2 and then 8 minus 4, 8 minus 6. That's it. As it's a even, the n value here is even, so we are going to multiply with pi by 2. Right, so let me write it here. So 8 minus 1, it will be 7. So 8 minus 3, 5. 8 minus 5, 3. 8 minus 7, it will be 1. Here it will be 8 and then 6 and then 4 and then 2 into pi by 2. So let's see, terms will be getting cancelled. So 3 here, 2 times. So 7 into 5, 35. So 35 pi divided by, so what are the remaining terms? So 8 into 2, 16 and then 4 into 2, 8. So 16 into 16 will be the thing, right? So sorry, into 8 is already there, right? So this 8 we have to multiply. So that I missed. So this entire 8 is also there. So which will be getting cancelled? 8. So 4 into 2, 8. 8 into 2, 16. 16 into 2, 32. So what is the final answer here? The final value of this integral will be equal to 35 pi by 32. That's it. So the only thing we should be aware here is the Wallis formula as well as the properties, where we have converted these limits from 0 to 4 pi to 0 to pi by 2 and we'll be having the 8 here. So I hope you guys got this one. Why you are getting 256? I guess you missed this 8 part. So if you multiplied this, you will be getting the answer. So most of you missed this 8, I know. So I also missed it here. So this 8 has to be multiplied because it's present in here. So if we multiply, the 256 which you got will be cancelled and you will be having the simplest version will be 35 pi by 32. So most of you has given the answer. But you just missed this 8. So I hope you can correct that part. Okay, so let's move on to next question. Similar type of question. So here it comes. So quickly do it. Okay, most of you got it. Quickly. So this is also same typical type. You can apply the properties here and get the answer. But you have to verify after substituting it whether you are getting f of x or minus f of x, because based upon that we'll be having the answer. So how we'll be verifying? So we have to check in place of x, that is 2 pi minus x, whether this is equal to f of x or not. Right, so that means cos of 2 pi minus x. So 2 pi minus x will be in the fourth quadrant, isn't it? So in fourth quadrant, cos will be, cosine function will be positive. Right. So, and here we are having 2 pi, which means there will not be any transformation. So, this will be equal to cos power 5x, which means when we substitute this 2 pi minus x, our f of 2 pi minus x will be equal to f of x, which means now how can we write this? So, we can write this to be 2 times of 0 to pi cos power 5x. Right. So, the next step will be, we have to verify by substituting pi minus x, so that we can convert this into pi by 2 or not. So let's just verify. So we have to check f of pi minus x, that is equal to cos pi minus x, right, cos power 5 pi minus x. So pi, that will be which quadrant? Pi minus x. So this will be pi here. Pi minus x will be in the second quadrant, isn't it? In the second quadrant, cosine function will be negative. Right, that means this will be minus cos x power 5, which means the power is actually odd, which means we'll be having minus cos power 5x. Right, so that means for f of pi minus x, we end up having minus f of x. Right, so when we have minus f of x, what we can do? We can directly substitute that this integral value will be equal to 0. Right, so whatever the constant here, it doesn't matter because the integral value itself here turning out to be 0. That means the value here will be equal to 0 directly. So this will be the answer of this integral. Okay, Siddharth has already given the answer. So I hope you got the idea of how to apply our properties. So after application of the properties, if required, how to apply our Wallis as well as the gamma formulas here. Right. So let's move on to the next concept, guys. That is nothing but limit as a sum. Right. So basically, what is the formula which we'll be using for this limit as a sum? Right. So what is this basically actually? To find the sum of an infinite series. Right. So there will be some infinite series. So if we want to find the sum of this infinite series, so we can actually normally can also find by using limits and all, but it will be a lengthy way. But we can convert that infinite series with the help of our definite integrals. We can convert that and we can simply find the answer using the concept of our definite integration. Right. So this will be the formula actually. So if we are having a limit n tends to infinity from r equal to 0 to n minus 1, f of r by n into 1 by n. So that integral sum of infinite terms can be rewritten in this format of definite integration. So in detail, let's see how can we convert that sum of infinite series into the definite integration format. So this is the following method we will be using to solve the questions. That means to convert the given infinite sum of series to the definite integration format. Right. So for any given series, first thing what we have to write is, we have to write the r minus 1th term or the rth term of the series. So this is the first step. So we have to express our given series in terms of the rth term. So that will be preferably good if we express that in terms of our rth term. That means we are going to express in the format of 1 by n f of r by x. Right. And then our series will be turning out to be limit n tends to infinity. And what are the limit values? That is r will be starting from 0 to n minus 1. And we'll be having the inside term functions f of r by n into 1 by n. So we are going to convert and write our infinite series in the format of 1 by n f of r by n. And after that we are going to apply this limit. Right. So if we could do this, and what we are going to substitute here to convert into definite integration. Right. So now what is the infinite series we are having? Limit n tends to infinity, r equal to 0 to n minus 1 and 1 by n f of r by n. Right. So in place of this limit tends to infinity and this sigma, we are going to replace with integral. Right. And then in place of r by n, we are going to replace with x. That means this term will become f of x. Right. And in place of 1 by n, we are going to replace with dx. And our limits will be here, if it is 0 to n minus 1, then it will be 0 to 1. So that will be our corresponding limits. Right. So that's why it is preferred that if we could express in terms of r equal to 0 to n minus 1, then correspondingly our limits will be 0 to 1. So if it's from 1 to n minus 2, something like that, so based accordingly, we can change the limits. But here in general, this limit of infinity can be converted into our definite integration, that is in the format of integration from 0 to 1 f of x dx. Right. So it will be easy once we do one simple question, one question related to this limit as sum, then you will be having the quick idea how to convert that. And once we converted that, we know how to do the definite integration part and find the value. So let me explain you this limit as a sum with a simple question by simply solving a question here. So here we can see a question that is for limit of. So here we have to find the value of limit n tends to infinity 1 by n plus 1 plus 1 by n plus 2 plus 1 by and so on 1 by 2n. So how can we write this actually? If we take the n value, so we have to represent in terms of our rth term. Right. So if I have written this, so n plus 1, n plus 2, n plus 3 and so on, it is going on. That means this is my r values. So I can write this to be limit n tends to infinity. Right. So this is sum of the terms. So I can add the sigma here because this is 1 by n plus 1, 1 by n plus 2. So this is nothing but summation of all these terms, right? So when we have this summation, what can we do? We'll be use the sigma here. Right. So sigma. So in place of this one, I am going to substitute r. So my r value will be here. So what is my r value starting from 1, 2 and so on, right? So my r value will be starting from 1. And what is my last term here? 2n. That means what is my r value? N plus n will be 2n. That means my r will be going until n. So here what I am doing, I am trying to convert my given sum of infinity series to sigma format, that is my summation. So limit n tends to infinity, I have remained as it is, and this entire series sum I am going to convert. So this is summation. So in place of 1, 2 and so on, I am going to replace with r. So r is varying from 1 to n and this function will be 1 by n plus r. Right. So if you could, if you expand this sigma, that is this summation, again you end up having the same series. Right. So this is my rth term, like I have converted here. So now what I'll do is I'll simplify it further. So limit n tends to infinity, sigma will vary from r equal to 1 to n. So in our previous format, what we have seen, it should be in the format of r by n. Right. So now what I'll do here, I'll take this n common from here. So if I take n common, what it will be here, it will be 1 and here it will be r by n. Yes or no? From this n plus r term, I have taken this n common. So now I can rewrite this in the format limit n tends to infinity, sigma r equal to from 1 to n. 1 by n I can write it separately and then 1 by 1 plus r by n. If you observe, this is in the standard format or not? Right. So according to our conversion of this limit to integration, definite integration, how will we doing that? So it will be in place of this limit and sigma, we are going to substitute this integral, and when r is starting from 1, the limits will be 0 and 1. So it will be 0 to 1. And in place of r by n, we are going to substitute x. That means it will become 1 by 1 plus x. And in place of 1 by n, we have to substitute dx. That means here it will be dx. So this entire sum of infinite series has been turned out to be integral of 0 to 1 by 1 plus x dx. So this will be my function. So what is integration of 1 by 1 plus x? That is nothing but log x. So it will be log 1 plus x. And what are the limits? 0 to 1. So let's substitute. That will be log 2 minus log 1. Right. So what is the value of log 1? So log 1 will be 0, which means directly it will be log 2. So here the sum of this given infinite series is nothing but directly equal to log 2. Right. So if we try and sort it out using this limits, it will be a bit lengthy. So instead of that, we can convert this into our definite integration format and we end up having our direct answer here. That will be a log 2 here. Right. Okay. So most of you has already solved it. So good. So let's just have one more question, because you should be knowing how to convert from this infinite series to our general format of limits, like our rth term. And once we are done that, the next step will be simply conversion of our nth rth term to our definite integration format. So let's just do one more question related to our limit as a sum. So here comes the next question, guys. Quickly do it. So most of you have solved the previous question also. Good. So let's see how many of you could able to solve this. Quickly, guys, can anyone tell me the integral format here for this? Take your time, do step by step, one by one. So here, what is the infinite series which they have given? Limit n tends to infinity, n by n plus 1 whole square plus n by n plus 2 whole square. So this limit n tends to infinity will be remaining as it is, and this has to be a summation. So we can use the sigma. So let's just take 2 more minutes and then you can simplify it. So this will be the summation here. So we have to use the sigma and we can take the r. So you can use the same thing. So r will be from 1 to n here. And what will be our function inside will be? It will be n by n plus r whole square. Right. So now we can actually rearrange this term. So just take your time and do it fast. So this will be limit n tends to infinity as it is. Sigma r will be from 1 to n as it is. And here our function should be in terms of r by n. So in the denominator, if you observe, it's a whole square. So from here we can take n square out as common, which here it will become 1 plus r by n whole square. Right. So now numerator n and the denominator n square. So 1 n will be getting cancelled and will be remaining with limit n tends to infinity sigma r equal to 1 to n, and then we'll be having 1 by n into 1 plus r by n whole square. So if you could able to get until this step, then the next step will be very easy, guys. So quickly do it, quickly solve this and let me know what's the answer. What is the sum of this infinite series? So if you could get until this rth term of our given infinite series, so the next step will be conversion of this infinite series, this rth term, into our definite integration format. So in place of this limit and sigma, we will be substituting this integral, and r is from 1, so it will be limit 0 to 1. And in place of 1 by n, we are going to substitute this dx, and here 1 by 1 plus, in place of r by n, we will be substituting x, so 1 by 1 plus x whole square. So this will be our function. That is, our definite integration here will be 0 to 1, 1 by 1 plus x whole square dx. So that will be our function. So this is our function, integral 0 to 1, 1 by 1 plus x whole square. And we know how to simplify and find the integral here, integral value. So let's see if anyone given the answer. No, it shouldn't be minus 1, Sham. Can you check it once? You're nearly, you are very nearer to the answer. Check it once. Maybe some calculation error. So it will be 1 by 1 plus x square will be minus 1 by 1 plus x. The integration of it will be. Right. And what are the limits? 0 to 1. So if I substitute 1 here, it will be minus 1 by 1 plus 1, 2. So minus of, if I substitute 0, it will be minus 1 by 1. Right, so it will be minus 1 by 2. So minus of minus plus 1. So 1 minus 1 by 2 will be 1 by 2. Why you are getting minus 1? Can you check once? I have explained you. So here it will be 0 to 1 and 1 by 1 plus x square will be our function. So let me erase this. So what is our definite integral function? We end up having 0 to 1, 1 by 1 plus x whole square. So we can take this as some x square and it will become x power minus 2. So then after integrating it, it will turn out to be minus 1 by 1 plus x will be the integration. That means limits will be 0 to 1. So let's substitute 1 here. That means 1 minus 1 by 1 plus 1. So minus of, so if we substitute 0, it will be minus 1 by 1. So this will be minus 1 by 2. So minus into minus, it will be plus 1. So 1 minus 1 by 2, that is 1 minus 1 by 2 here will be equal to 1 by 2. So that will be the final answer here. So the limit of this, the sum of this infinite series will be equal to 1 by 2. So I hope now you got the answer. So 2 of you has given the answer also. So this is how the only thing when it comes to limit of sum, we have to convert into the rth term, and then using the simple substitutions, we'll be converting that into our definite integration format, and then simply application of our definite integral, how we'll be solving it and finding the value. Okay, someone is asking to integrate it. Okay, let me just do the integration part. So 1 by 1 plus x whole square dx. Right, so this can be rewritten as integration of 1 plus x minus 2 dx. Right, so this is in the format of integration x power n. So what is integration of x power n? X power n plus 1 by n plus 1. Right, that means 1 plus x. So this is n plus 1 divided by n plus 1. That means here it will be 1 plus x. So 1 minus 2 will be minus 1. Here 1 minus 2 will be minus 1. Right, so this 1 plus x whole power minus 1 can be written as minus 1 by 1 plus x. So the integration here, so the integration of this 1 by 1 plus whole square will be equal to minus 1 by 1 plus x. Right, so I hope you guys got it. So let's do one last question, which is from our recent 2020 mains paper, and then we'll just wind up the session. So this is the recent 2020 question, JEE mains question, which is from the definite integrals concept. So quickly solve this, guys. So this question is related to the modulus function. So if you could split this integral according to the modulus, then the other thing will be the simple substitution of the values and all. So quickly, guys. So you have to look into the critical points. Here if you observe, there are two modulus, not a single one here. So you can start solving it by one. So first you can take this modulus, that is x minus 1, where the critical point will be 1. And once you could solve it, and then we can expand the other one. So let's start with the first modulus here, where the critical point will be x equal to 1. So quickly solve it, guys. So after expanding the first thing, what will be the next critical point you are getting? Can anyone tell me that? Or else you can tell me the intervals or the limits where you are actually getting the break here. So here we can see for the first modulus, the critical point will be 1. So let's break it at 1. So 0 to 1. So if we take the value 0 to 1, this will be whether the inside expression will be positive or negative. So x minus 1, it will be negative, right? So if we take values less than 1, so this will be negative, which means this x minus 1 will be converted to 1 minus x. And minus x is already there, dx. Right, so the other limit will be 1 to 2. So if we take any value 1 to 2, it will be positive only. So this will be x minus 1 minus x dx. So let's simplify this. So this will be 0 to 1 modulus of 1 minus 2x dx and here it will be plus x and minus x will be getting cancelled. We will be having minus 1, so which is 1, so 1 to 2 dx, right? So our second bracket we are having directly a dx, so no need to simplify it. But here if you observe, we are having one more modulus which the critical point will be, so here 1 minus 2x, so what will be the critical point? So x will be equal to 1 by 2. So now we have to split this at 1 by 2. So let me do it here. So the first will be from 0 to 1 by 2. So if we take any values from 0 to 1 by 2, what will be the first thing? Whether they will be like this or it will be a negative or positive. So 0 to 1 by 2, then it will be the positive only. So directly the function will be 1 minus 2x dx. And then if we take the next one, that is from 1 by 2 to 1, then what is the integration? So what is the value here? 1 minus 2x, whether it is a positive or negative. So it will be a negative. So then it will be turning out to be 2x minus 1 dx. Right. And the other term which we are having here will be integration 1 to 2 dx. Right. So these are the terms after splitting and breaking the terms here. Right. So we are having the integration that is 0 to, so let me write the final integration steps here. So they are from 0 to 1 by 2, which is 1 minus 2x dx, and the next will be 1 by 2 to 1, 2x minus 1 dx, plus integration from 1 to 2 dx. So these are our three terms which we are having after the splitting of this modulus function here. So here there are two modulus functions. After splitting it, this will be the term. So let's just integrate these terms and find out the final answer here. Can you guys do that integration part and let me know what's the final answer here quickly? So for the first one, it will be x, and here x square by 2, and that 2 will be getting cancelled. We will be remaining with x square, 0 to 1 by 2, plus here the same thing, x square minus x, and the limits are 1 by 2 to 1, and here it will be x and the limits are 1 to 2. So let's substitute the values. So it will be from 1 by 2. So 1 by 2 minus 1 by 4 here. So no need to substitute 0 because it will become anyways 0. And then here 1 by 4, sorry, it will be x square 1, right? So it will be 1 minus 1. So this will become 0, right? So 1 minus 1 will become 0. Minus, we have to substitute the next limit 1 by 2. That means 1 by 4 minus 1 by 2. So this is the integration part of the second term. And for the third term, it will be 2 minus 1. Right. So 1 by 2 minus 1 by 4 we are having here. 1 by 2 minus 1 by 4. So 1 minus 1 will be anyways 0. And then we are having minus 1 by 4 plus 1 by 2. Plus 2 minus 1 will be 1. So this term after expanding minus 1 by 4 plus 1 by 2. Right. So here we are having 1 by 2 plus 1 by 2, 1. So 1 plus 1 minus 2 by 4. Right. That is 2 minus 1 by 2. So 2 minus 1 by 2, what is the answer? LCM will be 2. So 4 minus 1, that is equal to 3 by 2. So what is the final value of this given definite integral? That will be equal to 3 by 2. So once we could able to split that at the given critical points, then it is easy to find the integral values directly. So I hope you guys got the some of you has given 1 and 1 by 2. Can you guys check the answer once again? Okay, now you have some are given 3 by 2. Okay. So the final we are having here is nothing but 3 by 2. So the integral value here will be 3 by 2. So it's the recent 2020 JEE mains question, guys. So this is how the questions from JEE will be there from the definite integrals. So you can think of in this difficulty level you can have, or else in this typical model you can expect. So yeah, most of you has given the answer. So that's all for today, guys. So with this, we have finished all our concepts related to the definite integrals part, and we have even covered questions for each of the corresponding concepts, and we have picked the questions from JEE paper of 2020, and we have solved that also. So that's it for our definite integrals and for our today's session. So in our next session, we are going to start with the next chapter. So maybe the next chapter will be, so as we have covered both the integrals, that is our indefinite integrals as well as the definite integrals. So the next part will be our application part of integrals. So that we are going to cover, and we are going to start in our next session. So in our next session, we'll be starting the application part of the integrals. So I hope you guys have understood today's session. So if you can go through the session later again, once again, and if you have any questions, you can let me know, and we can have a discussion and clear out your doubts. So that's all for today, guys. So we'll just start our application part of integrals in our next session. Thank you.